In this video, we're going to talk about two special objects, lists and data frames, which are very specific to R. So let me start with a reminder of the notion of vectors in R. In a previous video, I mentioned that there are two main flavors of vectors. On one hand, you have what it's called the atomic vectors, and this is probably the traditional way in which most users refer to vectors in R. But technically speaking, we have another flavor, we have another class of vectors, which are the so-called non-atomic vectors, better known as lists. So here's where you will find the R lists. To give you a sort of mental picture, the way I like to display vectors is as something like this, a contiguous set of cells, whereas for non-atomic vectors or lists, the way I like to depict them is something like this, in which you have cells containing data, but in a discontinuous way. Contiguous cells, the atomic vectors, whereas in this case, you have non-contiguous cells. So that's one of the differences. Again, this is just my opinionated version for how you could picture in your head what these two kind of vectors may look like. And then also, just to reiterate the idea of atomic data, atomic vectors. So the term atomic means that all of the data types, all of the elements inside a vector must be of the same type. It has to be a homogeneous structure. If you try to mix or to combine two or more different data types in a single vector, what R will do, it's going to apply its famous implicit coercion rules. So here's an example. Let's say you have a vector, let's call it X, and in this guy, we're going to combine a logical value, true, for example, an integer value, the one integer with 1 and capital L appended to it, and then let's say a double or real value 2.5, for example. So we have a logical value, integer value, double value. As you know, when R combines these guys into a single vector, the data type that has the highest priority, which is the double 2.5, will dominate, and therefore the whole vector is going to be of double data type. Now, what if you want to, let's say, maintain the data type of each of these elements? Well, this is where you're going to use lists. So an example, let me create an object called LIS, lists, as an abbreviation for list. And then I'm going to use the function list. This is the main function that allows you to create lists in R. And I can pass a true value, logical value. Then let's also insert the integer value. And finally, the double value. Each of the individual elements actually gets to keep its data type. So again, just to give you an illustration, a mental picture, you're going to have the vector containing the true value, the logical value, another vector containing the integer value, and then, of course, a third element, third vector containing the real value. And then, again, this is just my opinionated way of what an R list may look like. So I'm going to draw another rectangle wrapping the green guys, and then let me connect them with lines, again, just to indicate the idea that you have some object that its elements are not exactly contiguous. And in this way, you have two things. So you have the, let me call them, you have the blue boxes or the blue containers, and then you have the green boxes or the green containers. The way I like to think of a list, again, using this mental picture, it's to think of it as a train with wagons, so train with cars. So the cars, the wagons, are going to be the blue boxes, And then inside the wagons, inside the cars, you have other objects. So those are going to be the green ones. And very interestingly, I don't have it in this example, but a list can contain another list inside of it. So one of the green boxes can be another list. So this is nice because it allows you to have an object in which you can have a very nested, very embedded structure to handle pretty much any type of data object in R. Now, every time you print, in other words, you type the name of a list in R, and again, pretend that you're looking at the console. So this angle bracket would be the prompt, and then you type the name of your list. In our case, let's use our previous LIS list. So the way R will display its content, it's something interesting. What you will see on the screen, it's going to be something like this. You're going to find double brackets, and then in this example, a number 1, and then another set of closing double brackets. And then below, you're going to find single brackets starting at position 1. And because the first element is just the true value, you will see that value display on the screen. And then you're going to find another set of double brackets with the second element. This guy contains just the integer 1, and finally a third set of double brackets indicating the third element of your list, and in this case is going to be 2.5. What you have here with double brackets, think of this, or this would correspond to the wagons of the train. And then inside these guys, you're going to find the actual things contained in the wagons. In this case, each of them is a single vector with just one element, one logical, the true guy, one integer, the 1, and then a double, the 2.5. Very often, you're going to want to give names to the elements in a list. So for example, I could, let me just recreate the previous example with the list LIS. Again, using the list function, I can give simple names. Let me give name letter A for the logical value true. Let me use the name letter B for the integer 1, and finally letter C for the double value 2.5. This is one way to give names. Another equivalent way to create a list in which you provide names to their elements is, again, using letter A without quoting. So just simply type A equals, and then you indicate what value is given that name. B, again, without quotes, equals 1 integer, and finally C equals 2.5. So these are two exactly equivalent ways to create a list in which all the elements will be named. And when you have a list that has named elements, every time you print this guy in the console, what R will display is, it won't use the double brackets anymore. What it will use is the $sign. Next to the $sign, the corresponding name of that element, and then down below, well, the content of what is stored in that position. So you will find $A, $B, that's going to be our integer 1, and then finally $C, that's going to be the double value 2.5. My recommendation in general is, whenever possible, give names to the elements in your list. And this will help you a lot in terms of manipulation and referring to the objects in a list in a more transparent, in a more descriptive way. Let me just mention a couple of additional examples in which we're not storing just a single vector. You could have, and I'm going to write this in a pictorial format. You could have, say, a vector of any class, of any data type, 3 elements. Let's say you have 3 elements. You could have, for instance, a matrix. Let's take a matrix with 3 rows, 3 columns, a 3 by 3 matrix, for instance. And you could also have, let me include, let's say, another list. This is going to be a 2-element list. and then put these three guys inside a list. So again, using the analogy of the train, you would have the first wagon containing the vector, the second wagon containing the matrix, and the third wagon containing another list of two wagons. So this is, again, another example of what a list may look like that has different types of objects. They could potentially be of different data types. This could be, let's say, this could be a character vector. This could be a numeric matrix, integer or double. And you could have another list, perhaps containing, perhaps here you may have another matrix, and over here you may have another list. Obviously, this is going to be a more embedded structure, more nested structure, but there is no limit into what things you can store inside the wagons of your list.